Hello and welcome to Chapter 7 on normal distributions. Today we will be talking about continuous distributions as well. So normal is going to be our first example of a continuous distribution. The normal distribution is probably the most widely used distribution of all of statistics. So just as a quick reminder, distributions do two things. They tell you what values a random variable takes on and how often it occurs, and it does that by assigning a probability. So when we talk about the normal distribution, it's completely described by two distinct parameters: the mean, or the center of the distribution, which is the mean, mu, and the standard deviation, sigma. That's the mean right there, and then the standard deviation. So these will typically be values given to you as you approach a problem. Anyway, so be thinking about, oh, if these are always the same, how on earth is just two things going to give me what this looks like? And that's really because the normal distribution has three distinct characteristics that it always has. It's always symmetric, it's always bell-shaped, and it's always unimodal. Knowing that it has those three characteristics, once you know the mean, aka the center, and how far it's spread, and that it has to look symmetric, has to have a bell shape, and has to have one peak, aka unimodal, you know exactly what this looks like, and it always looks the same. Now, how it looks different depends on the value of the mean and the standard deviation. So when looking at changing just the standard deviation, but keeping the mean the same, that keeps your center the same and then changes your spread. So in this graph below, I have three distributions all with the same mean, 15, and all with different standard deviations. One has 2, one has 4, and one has 6. So as you look at this, one of these curves is more spread out than the other, aka its spread is further away from the center. I'm hoping you notice that is the red curve. And then the blue curve has the least amount of spread because its data is in tighter and closer together. And then the green kind of falls in between those two. So that tells you the 2 is the blue curve and the green is the 4. So, and if you're wondering why the peak is going down, well, I'll tell you why in a minute. Let's look at how things change if you mess with the mean. If you keep your standard deviations all the same, so I picked 3 here, and then vary your mean, so I picked 10, 15, and 20, you'll notice that your three different curves look different. So which curve has the mean of 10? Which has 20? Which one has 15? And knowing what you know about the number line, you're hopefully picking out the fact that, oh, well, shouldn't it just go in order? Well, it's a little bit more than that. I'm hoping you notice that the mean for the blue one follows the peak, and that looks to be at 10, looks to be at 15, and looks to be at 20. It's the center, just like we would expect the mean, especially for something symmetric. So I'm hoping you notice the mean tells you something about the position of the center of the distribution. Don't forget, bell shape, spread. Okay, so combining what we just saw, here's what we know. It's symmetric about the mean. The mean and median are always going to be the same because of the symmetry. And the highest point occurs at the mean. The total area under the curve, the total area under the curve has to be 1. That's the law of total probability, that everything must add up to account for everything possible, aka 100%. So the total area is 1. That's why when we were looking earlier at changing spread, the height of the bell had to go down because they all had to take up the same amount of area. Or the amount of paint it would take to fill those curves was the same. And then the other thing to note is the area to the left of the mean, aka the lower half, is going to be same as the area to the right of the mean, the upper half. So these have to be the same, and since it must add up to 1 and these halves have to be exactly the same because of symmetry, the area must be 50%. That guy, 0.5. All right. So why on earth are we talking about this? Well, we talked earlier about how we use the standard deviation as a ruler. Z-scores provided us a standard way to compare values, and really it tells us the number of standard deviations away from the mean. That's what a z-score's purpose is. Well, it actually has a little more purpose than that when it comes to dealing with the standard normal curve. So when it comes to z-scores, we really use them to tell how different is our value from other values. Let's look at an example in case you forgot how to do a z-score. When you combine z-scores with the normal curve, you get the following standard characteristics. This used to be called the empirical rule, but we call it now the 68, 95, 99.7 rule. So if I have a normal distribution, aka something with unimodal, symmetry, and, well, a bell shape, we know that 68% of all values, and notice this is about here because we're rounding a little bit, fall within one standard deviation of the mean. That's to say that when I look at the standard deviation. Sorry, one standard deviation each direction. So I'm starting at the mean, center line right here, and I go one standard deviation below. So I'm coloring one standard deviation below and one standard deviation above. I get 68%. Get the idea? Okay. When I go two standard deviations above and 2 below, I get 95% of everything. So 2 above, this is going to get real dark real quick. 2 below, that's 98% of all scores. Aha. Now, if I go even further out, so I'm going to run out of colors here that actually work, sorry. Out to 3. Okay, this is not going as planned. You get the idea. If I go 3 away, I get 99.7 of all values. So this is why earlier in the semester I told you that when we look at values that are more than 3 standard deviations away from the mean, so larger than 3 in the positive direction and smaller than -3 in the negative direction, those are very unusual. How often do they happen? Well, if you're dealing with a normal distribution, it's like less than 0.3% of the time, or in case that wasn't clear, 0.003. It's not very big. There's not a lot out there in those tails. And if you're more than 2 away, you're in the upper and lower 5%. There's not very many. That's why it's considered unusual, not very unusual, unlike the 3 away. And then the ones around 1 standard deviation away are pretty common. And we use this to make decisions about whether or not something was unusual. That still applies. So, for example, on August 8th in 2001, the Dow Jones Industrial Average dropped by 634.8 points, sending stock waves through this financial community. This is very dramatic, except for, is that really a big drop in that year? I don't really know. We'd have to compare it to the data for the rest of that year. So in the mid-2011 to 2012 range, the mean daily change for the Dow was 1.87 points. It's not very much. It's a small mean, Okay, but that's all right because remember, this is a drop, I'm going negative. And then the standard deviation is huge. It's 355.28 points. As you look at that, keep in mind, this tells us about how unusual 634.8 is as a drop. So let's see what the z-score is so we can decide whether or not it actually is extraordinary, because it probably is. We'll see. Yeah, let's actually come up with some statistics. You mean, this is all great and everything, just looking at it and being like, oh, that's a big number. But we're better than that. We can actually use statistics to say this is unusual. So what we'll do is we'll convert this into a z-score. We subtract the mean and then divide by the standard deviation and come up with a z-score of -4.10. That tells us that this is more than 3 standard deviations below the mean. Why is that important? Well, that also tells us a relative probability of how likely it is this is to happen. That's pretty tiny. Yeah, because this is on the negative side. This is the less than 3%, thanks to the 68, 95, 99.7 rule. Real quickly, since this is below -3, it's in the extreme tails. We know that this is a very unlikely event. That really was extraordinary. Take a special note that since this was a drop, the value we use here is negative. Watch out for this in your homework. Occasionally they use the word decrease, drop, reduced. They mean it's negative. Okay. So when we're describing what the normal distribution looks like, we write it out as n, meaning this is normal, this is what the mean is, and this is what the standard deviation is. The reason we write it this way is because, well, it just takes forever to write it's normal, blah, 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 especially since we will be using it for the rest of the class. And any of you taking Stats 2, this is literally where Stats 2 will pick up. Hey, we use the normal distribution, we're going to use it to calculate stuff. Since it comes up so frequently, we came up with a shorthand for it. So when you see this symbology, I want you to think this means it is normal with mean mu, standard deviation sigma. So I've given you an example below. For example, IQ scores are normally distributed with a mean of 100 and standard deviation of 15. We usually write that as just that, as n 115. It's much shorter since we know it. We're going to use this a lot. It gets used a lot in general. That's why it gets its own chapter. Anyway, because the total area of the curve is 1, there's a correspondence between area and probability. This is the same correspondence we were using in chapter 6 to decide area for discrete probabilities. It's exactly the same. The difference being this time it is continuous, so it's a smooth curve, so there aren't blocks. So when we do area, it's going to look like what I was coloring before, where you'll draw a line for a specific z-score value and then figure out the area less than it or greater than it or whatever and whatnot. Coloring on this is not as easy as I thought. Okay. Let's do an example. The serum cholesterol total for males 20 to 29 years old is known to be normally distributed with a mean of 180 and a standard deviation of 36.2. This is from the National Health and Nutrition Examine Survey. An individual with a total cholesterol greater than 200 is considered to have high cholesterol. Shade this region on the normal curve. So suppose the area under the normal curve to the right of 200 is 2.090. Provide an interpretation of the results. So I told you what the probability is. Let's talk about this. So in drawing it, and this is exactly an output from Minitab, so I'll show you how to do this in a minute. So this tells us that the probability that a randomly selected 20 to 29-year-old male has high cholesterol 0.290% of the time. Or if you want, you can use the percentage description under here. The proportion of 20 to 29-year-olds that are male that have high cholesterol is 0.29 or 29%. So really, you want to think of the area under the curve as a probability or a proportion, but not really anything else. So keep that in mind. So if you're thinking, hey, all these guys look the same, they have the same characteristics, they all have it, but it varies a little based on center and standard deviation. Well, that's exactly what your average individual was thinking, like back in this was sometime in the 1800s, who was doing statistics, because they realized, oh, well, can't we just have a standard that they all based on? And yeah, you're thinking exactly like they were. So if we standardize using z-scores, aka I take any distribution in the world and I find the z-scores associated with it, so I take any score, subtract the mean, and divide by standard deviation, I get the standard normal curve. Yep, standardizes everything. They all look the same. So if you make this conversion, subtract the mean, divide by the standard deviation, you get the standard normal, which has mean 0 and standard deviation 1. The idea being that, oh, I'm just doing the z-score. It's my distances from the mean. My standard deviation's away from the mean. And it tells you where you fall on this distribution, the standardized one. So we're going to use Minitab to find some probabilities under the standard normal curve. So we know it has mean 0 and standard deviation 1. We want to find a couple different things. We want to find the area to the left of the z-score of 1.25, find area to the right of 0.57, and then to the area in between 0.45 and 1.3. Here's how you would do that on Minitab 17 and Minitab Express. So what we would do is we'd select normal from the distribution center values, mean and standard deviation. We'd choose shaded area and then click on X value. I have several videos on how to do this. I'm going to talk to you about the results that we see from doing this next. And remember, this is a standard normal, so it has mean 0 and standard deviation 1. Here's a little bit of what you would look like. So if you're finding the area to the left of a particular z-score, this is what you should be picturing in your mind for what this looks like. And this right here is the score you would get. That's what the probability value is. And notice where your score lies. So there's your z-score. And then here is your probability. Up above, circled. So when you're trying to find area to the right, here's what it would look like. And you'd come up with 0.2843. Here's what the in-between value will look like. So if you need to find out what's going on between two scores, you would be using Minitab's probability distribution plot to do that as well. Okay, so for any continuous random variable, the probability of observing a specific value of a random variable is 0. Why? Because this is all area. When you're dealing with area, the area below a value, a single value, is a line. Lines don't have area, they're one-dimensional. They have 0 probability. So whether or not an equal sign is present no longer matters. So when you're dealing with a continuous random variable, the only thing that matters is the less thans and the equal tos, which I've written below. So as you look at this, keep in mind that we don't care if the equal value is present. It's not going to produce or change anything. We only care about, are you shading the right direction or the in-between values correctly? Okay, so let's look at going the other way around. So let's use Minitab to find a z-score given an area probability. So find a z-score to the area to the left of the z-score 0.325. So if you're trying to picture this, let me draw this. So you've got your standard normal curve, woohoo, and there's 0 because that's the mean. We want to find the score, and I'm trying to draw this accurately because I know that this half of the graph is 50%. So I don't know. Oh wait, that's the one I don't know. I don't know the score, but I know this area is 0.325. So I'm trying to find the score that associates with that. So it's kind of like going backwards. I know a probability, I want to find a score. Similarly, if you want to find the z-score for the 25th percentile, that's the same thing as finding Q1, by the way. Oh, I didn't change colors. There's mean 0. I want to find the score so that, question mark, I get the lower 25% or the 25th percentile, 0.25. Oh, my handwriting looks great. Similarly, if you wanted to know the upper quartile, you could do the lower 75% or the upper 25% to figure that out. Let's see how that looks on Minitab. Come on. Here we go. So similarly, we're going to choose graph probability, distribution plot, view probability once again. However, the only difference here is that instead of shaded area, we're going to choose probability. So we want to choose the probability value and then enter it in as a decimal and use it to find the associated score that goes with that particular probability. And you got to be very careful to make sure you're selecting the right direction when it comes to your shading to make sure this works correctly. So here's the first one. So we want to find the z-score associated with the area so that the area to the left of the z-score is 0.325. So there's the z-score that works with this. So there's our answer, there's our z. And notice that up above we have the correct area listed here. Areas always appear above in Minitab, and those are our probabilities. So our probabilities always appear above. Similarly, for the 25th percentile, you shouldn't be too surprised that it's negative since you know that the lower half of the distribution is 50%. You cut that in half and there's what you get. So there's that guy. Smiley face, Z. I don't know why I'm happy about Z. Okay. The last thing that you can use standardization for is deciding whether or not a particular set of data looks normal. So this is what's called a normal probability plot, or a QQ plot as it used to be called. And so what you do is you take a distribution's value, so I've got that over here on the left, and you compare it against their normal probability scores if it were a perfectly normal bell curve. Because the reality of the world is, hey, your data isn't perfect. It's probably not going to come out nice. And it might not look perfectly normal. So in particular, this is the Nissan Maxima data. I do believe these are gas mileages. Yes, okay. And so kind of tilt your head to the left and you'll look at that and you're like, oh, well, it's kind of normal, but it's got some tail issues. It's not quite symmetric. So, you know, I'm wondering if that's going to be reflected in the normal plot. And it's got a little bit of a lump there. Oh, I'm a little worried. All right. I've over-described this. So what does this translate to in your QQ plot? Or, sorry, I keep calling it the old name. Your normal probability plot. You want to see a straight line here, because that means it's linearly associated to being normal. And if it doesn't have a straight perfect line, then it's not perfectly normal. Now, normal raw data doesn't look perfect. It rarely ever looks absolutely excellent. So I'm hoping you notice there's a couple points down here that look non-normal. This curves away a little bit. So I would say that these areas are very non-normal looking. And the good news is that I shouldn't call them ancient, the early statisticians of our era knew that raw data rarely looks perfect. So a lot of the methods we're going to use going forward only need it to look kind of normal, so normal enough. And this would qualify because it's normal except for a couple places on the extremes. And it would be fine to use all those methods on that we do in like chapter 9, 10, and 11. And that's the good news, because without that, oh boy, this would be a mess. Okay, so here's one that looks a little bit worse. So as you can see, these weights data from men is very skewed, and in particular this is skewed to the right. If you're having a hard time picturing this, tilt your head so that the positive end is where the positive end should be. So I'm sorry, the larger end should be where facing positive. So this looks kind of, there's my one peak kind of deal. There's my tail. So this is very non-symmetric looking, and you see how the normal plot looks curved here and curved out even more and has an extreme value. It doesn't look straight, so this is very non-normal. Which, we also call just skew. Skewed. Yep. So the normal plot is nice because it's going to help you recognize skewness a little bit better and how far off from normal you are. So the previous example, yeah, it was normal enough to be okay. This one, not so much. Alrighty. So the one real awesome use of the normal distribution is you can actually use it to approximate a couple other distributions. So previously we've dealt with the binomial a lot because the binomial shows up a lot and it's discrete. Discrete has some negatives though, because not everything in the world is ruled by whole numbers. In particular, when you're looking at a binomial, you can either have yes or no, success or failure, and that's it. And if you're counting stuff, you can't have parts and partials, and sometimes that's a little bit difficult to deal with. It's also, in general, really difficult to reverse the binomial. One of the things we did a few minutes ago was we looked at an example where we had some probabilities that we knew or wanted, and we want to know the score associated with them. That's not estimated really, really well by the binomial because it uses whole numbers. So we can use the normal to approximate the binomial as long as a couple things hold true. And that's this one condition right here. So we can use the normal approximation of the binomial as long as we have at least 10 successes and 10 failures. If it fails to do either of these, we can't use the approximation. So again, approximation, be thinking like estimating the binomial using the normal, because the normal is a little bit easier to use. When you do that, the normal distribution has mean NP. That shouldn't be too surprising because that was the mean of the binomial as well. And standard deviation, square root of NPQ, which was the sorry, the standard deviation of the binomial. Oh, so the mean's the mean and the standard deviation is the standard deviation? Not too surprising. Okay, so here's a look at what this looks like. I wish I would have made that graph bigger. Regrets. Okay, so here's an example. Suppose you're finding a prize in a cereal box, and it happens about 20% of the time. If you open 100 boxes, what's the probability that exactly 15 of those you have opened has a prize? So here's what we're looking at. It's a binomial. My n is 100, my p is 0.20, and my number of successes that I'm interested in is 15. So if you did this with the binomial, this is what it would look like. So I've got the binomial graph over here. I'm hoping as you look at this, you notice, oh my, that looks very normal. And we can actually check that it's normal too. Sorry. I'm going to pause this for a minute. Okay, so again, looks pretty nearly normal. Well, it meets our conditions. It's at least 10 successes and 10 failures. I'm hoping you notice that NP is 100 times 0.20, which would give us 20, and NQ, aka number of failures, would be 100 times 0.80, which would be 80. And since these are both greater than or equal to 10, we're good to go, and it's going to look normal. And I'm hoping you do look at that and notice it does look super normal. So, not too surprising that you should use the normal for this. Moving on. Oh, fudge. I didn't realize I had that on the next slide. Oh, well. Yay! It works! Okay, so what's the mean? It's NP. So 100 times 0.20, which is 20. What's the spread? So you do n times p times q, and you come up with 16, and then you take the square root, and you get 4. And I'm hoping that as you see this, you're like, oh, so that's the center, that's the spread. That kind of looks like the graph I just had when we looked at it center and spread. So we're going to use the normal version on top of this real quick. So if I instead use the normal distribution to do this, so here's my center, and here's my spreads, and you're going to look at this and be like, what on earth is happening here? Sorry. God. You're like, okay, in the binomial I wanted to do the probability that x is 15, but it was a brick. So what's happening here? Well, 15 is directly the center of this brick on the binomial. So if I want to do a brick with width 1 in the normal, I have to go a half above and half below in order to come up with the normal approximation of it. So if you want to do exactly 15, well, I got to do from 14.5 to 15.5 because the normal probability does a continuous stream of distribution and it needs to account for that brick size. So it comes up with 0.046 or 4.6%. It's pretty close. Here's an overlay of the two of them on top of each other. So again, we were looking at the box 15. And the reason I have to do from 14.5 to 15.5 is to get the edges of that box with the normal version. Neat, huh? So this is a way you can use the normal distribution to approximate the binomial. You can also look at this and tell me exactly how much it's off by. So notice I'm above a little bit right here, and then there's a little hole right there that tells you that, oh, it's both a little bit off in both directions, but it's probably it's probably an underestimate using the normal distribution since the red line lies mostly below the blue rectangle. So it's not perfect, it's an approximation, it's an estimate. Anyway, fun fact, it's not just the normal distribution we're going to be talking about. There are other models that are continuous that work a little bit better and do well for different situations, and we're going to look at two. There are others besides this, just so you know. These are the two you're most likely to see in your mathematical future. Not all of you will encounter these. The first one being the uniform and the second one being the exponential. And we're also going to talk about typical situations these get used for. Let's have a looky-see. So the uniform distribution, we've seen once before, haven't we? You're thinking back to those dice, like 1/6. But this is the continuous version. So notice there isn't a set like count of 1, 2, 3, 4, 5 along that horizontal axis right here. So I'm talking like right here. You could be any value between A and B. Any value whatsoever. So it's a continuous possibility or infinite number of possibilities between A and B, not just 1, 2, 3, 4, 5, 6, which you can count. So since it's a continuous array, there's a continuous number in between. So when you're looking at, oh, well, how much area is there? Or if you want to find the probability that you're between like two values C and D, I'm just going to plot these on here. Here's C, here's D. The area in between them would be this little rectangle. I'm doing a terrible job of coloring here today so that you'll understand where this comes from. So remember, area, just the rectangle. How tall is the rectangle? Well, it's, 1 times B over A. So there's height, B minus A, height, times width, right? How wide is the rectangle? Well, it's how far C and D are apart, or D minus C. Ta-da! Oh, that was a minus. It didn't come out good. Why am I scribbling? It's just worse. Sorry, D minus C, which when you multiply those together, you get the following. That's it. Okay. What's the center? Well, it's halfway between A and B. It's the average of the two of them. What's the spread? Well, that one's much harder to do, but you totally can do it if you want to. I'm not doing that one. Accept it. Seeing this formula requires a little bit of calculus. It'll be okay. I think there's an algebra explanation of it, but it's not very clear. But just so you know, there's the two values. Again, don't worry about memorizing these. You can use formulas on your exams as always. Let's do an example. So suppose you arrive at a bus stop and you want to know how long you'll wait for the bus. P.S. That's also the typical for this. It's used for waiting time. So if you're picturing other examples of this, it's how long before you need to help a customer is a typical one for this, or how long before you receive another service call and things like that for business applications. Anyway, so you see a sign that says the bus arrives about every 20 minutes. So you assume the arrival of buses is equally likely to be anywhere in the next 20 minutes. So anywhere from 0 to 20. Woohoo! And it's uniform. So what's its height? Well, I need this all to be area 1. So 20 minus 0 times, I don't know what, the height h is 1. You solve for h. That gives you h is 1/20th, which is where this value is coming from, that 0.025, or right here. There's the function for it in case you care. We want to find the mean and the standard deviation. So we're going to use the formulas from the previous slide to do this. So it's going to be the average of your waiting time for the mean, which is 20 plus 0 divided by 2. So you should expect to, on average, wait 10 minutes for the bus. And then the variance is just b minus a squared divided by 12. And if you take the square root of that, you get 5.77 minutes. So it tells you your average is going to be 10 minutes. And the spread of this is about 6 minutes. So there's some variation here, and it's quite large. You might be only waiting 4 minutes. The exponential is the time until extreme event. So usually these are unlikely events like a 100-year flood or natural disasters, or it's a very strange, infrequent event. So although it's used for that, it's also used for very mundane things like how long until your light bulb burns out and stuff like that. And lambda is your average time between events. This is rating terribly. Anyway, this will make more sense when we do an example. And usually this is mainly focused on time between two events, or how long between two things happen, because that's simply just doing area on this distribution, which is just doing a subtraction. So it's a little bit easier on the exponential. Oh wait, that's on my next slide. So to find the probability between any two values, you're going to just subtract them from each other. Woohoo! The exponential is a little easier to use as long as you know its formulas, which is kind of nice. Let's do an example so you can see how this goes. So if a website experiences 4 hits per minute, and what's the probability? So notice that this is an average. It's how many happen per minute. That's how you know this is lambda. What is the probability we'll have to wait less than 20 seconds, aka a third of a minute, between 2 hits? So it's between less than 20 seconds tells you that it's somewhere between 0 and a third. So watch your units on these, because they're always times, and sometimes they're measured very differently. Since this one is in minutes, and we want to make sure we don't do this in seconds but do it in minutes instead. And then you just use your handy dandy handheld calculator to use the formula. So there's our 4, our lambda, and there's our 1/3, and there's our 0, aka our s and our t. Anything to the 0 power is 1. That's why we have a 1 there. And you're just going to subtract these two. So 73.6, or we can expect to wait about 20 seconds or less between hits about 73.6% of the time. And if you're wondering why that's such a large percent, remember what this guy looks like. He's heavy on one side, very unlikely on the other. Yep. Cool beans. Okay. Remember, these are just models. They're an imperfect representation. Sorry, they're a perfect representation to an imperfect situation. They're meant to guide us. They're not perfect. Don't assume everything's normal. Normal is like one of 6 distributions we've done so far. Don't assume everything looks the same. Don't use the normal approximation when you have a small sample, because it usually just doesn't work at all. All right, what else have we learned? We learned how to calculate some things on the normal distribution. I have lots of example videos on how to do lots of these coming up, so make sure that you know how to do them using technology. You can do the table version of this and the calculator version of this. I have videos on all of that. I highly recommend using Minitab for these because it is much faster and a little more visual, depending on who you are. That's not to say you can't do these by hand. You definitely can't. Can. Words. We can also use the 68, 95, 99.7 rule as a rule of thumb to judge whether or not a value is extreme, along with the z-score. So don't forget about that. We also need to be able to use technology to calculate other things with probability